then 12, and then 12 into would be 6 and 2, which is 3 and 2, so it would be 2 to the third times 3.
Good. So you know what you're saying, but to explain it's a little more difficult, right?
Yeah.
So what he's trying to explain is the fact that when you find the prime factorization of something, you're simply looking for prime numbers that could be written as some sort of a product to give you the original number you had. Right? So whenever you look for prime factorization, it means break it into, as Inigo mentioned, the smallest components. It's fundamentals, or it's like building blocks. Okay, your prime numbers are really the basics of all things. I happen to be watching, what is it? I think Jon Stewart, one of the talk shows, and this recent this guy that works at Caltech is considered to be like one of the smartest mathematicians in the world. Was on the show the other night, and what he studies like his interest is prime numbers, which is really, and if you think about it, like that's kind of boring because prime numbers, like what's exciting about that? But what he was talking about were things like twin primes and cousin primes and what are called sex primes, which are, and I'll explain that's not what you think it is. But twin primes, the idea is like 11 and 13. 11 and 13 only have one number in between them. They're a twin prime. Can you think of another twin prime? Another twin prime? It's not easy. It's not as easy as it sounds. And I mean, some of the smaller numbers, obviously, because they don't have any numbers besides themselves, but maybe above 11 and 13. What's another example of a twin prime? Like, for example, 11 and 17 would not be a twin prime. Or 13 and 17 would not be a twin prime, because 15 is in between them.
17 and 19.
17 and 19 is a twin prime?
It's 29 and 31.
29 and 31 would be a twin prime, yeah? So what he notices, though, what this mathematician studies, is the fact that twin primes become less and less frequently occurring as you increase numbers. Why would that be? Think about how factoring really works. Why would twin primes become less occurring or less frequently occurring as you increase in the number set?
Well, because if they all need to...
Like, for example...
I mean, the bigger the number is, the easier it is to fit numbers into it.
Yes, the larger the number gets, the more possibility or probability that a number is a factor of it. So even odd numbers that are really great numbers, there's a good chance another smaller odd number goes into it. So what he's noticed is that the distance between twin primes increases as the numbers increase as well. And one of the theorems that they're trying to figure out is, are there an infinite amount of twin primes, or are there a finite number of twin primes? And if you just think about it real quick, you probably say, oh, it's infinite, because if there are an infinite amount of numbers, then there must be an infinite amount of twin primes. But the question also is, when do twin primes stop existing? Above a certain amount, are there no longer any twin primes at all? Is that possible? So that's what his research actually is in, which is, it's kind of crazy to think about that. And then cousin primes would be like 13 and 17, because 15, the odd number in between them, it's in between, happens to be non-prime. So 13 and 17 are distance of 4 apart, we call them cousin primes. And then if they're 6 apart, that's what the term sex primes comes from, they're 6 apart. But the idea of prime factorization is where factoring comes from, right? It's breaking things into their fundamental building blocks. So this is analogous to something like chemistry, right? If you think about what makes up an atom or what makes up an element, you're looking at the fundamental parts of it. That's what factoring is. You're breaking things into fundamental parts. Why do you factor? Why? You know? Do you not know why you factor? Have you ever been told why you factor? Or do you understand? Or can you conceive why is it that you factor? What's the reason for it? It's not just so you can learn more math skills. It's a reason that you factor things. Nobody has a guess as to why you would factor? How about this? Where have you used factoring before in your other classes then? In your previous math class, you probably learned how to factor basic stuff at least. Where have you used that? With variables, not just numbers. Simplification. Good. Very good, because if you have a numerator and a denominator and they can be factored, there's a chance a factor might appear in both and then they can cancel, right? That's one reason, simplification. Another? There's another reason that's probably the most important. It's the reasoning factor, actually, the other one. Simplification for sure, but there's others. Yeah? They get a hand.
Is it to find the greatest compact between?
Good. So you need to find the greatest common factor to pull it out, but what does that lead you to? For example, if I had this, x squared plus 5x equals 0, why am I going to factor out an x? James just said to find the greatest common factor there. But why am I going to take out a greatest common factor of x? Why am I going to rewrite this as this? What does that do for me by doing that? And we're going to see this later in this section, in like 4.7 and 4.8, those sections. Jeff, go grab a little bit of water, please. Why? Just give yourself a little break, okay? Why would we factor this? What's the reason for it? What can I do now that I'm at this stage? What can I do? Alex?
You can move the x to the other side.
I can't, unfortunately, because it's multiplying. It's not a plus sign.
Dividing.
If I divide by x, it's 0 divided by x, and that's still 0. You're on the right track what you're trying to do there. If you were able to do that, Alex, to divide by x, you'd be left with this, right? And then what could you tell me?
You can move the 5 to the other side for x.
So really, you factor to solve equations. That's the whole key to factoring. The reason you're factoring is to solve equations. The reason you're factoring is to solve equations, okay? I mean, yeah, you're going to simplify things along the way, but usually, or 9 out of 10 times, the reason you're factoring is to get an answer to an equation you cannot get by simply looking at it. It needs to be simplified and factored, both. So let's take a look at what we're going to do today then. First term we're going to take a look in the first definition is what James mentioned a moment ago, greatest common factor. And it's what it sounds like. It's the factor that's common to all elements. So for example, what are the greatest common factors of, or what is the greatest common factor of 24 and 36? What's your greatest common factor of 24 and 36? 12. Why 12? Why not 4? Because 4 goes into both of these, doesn't it? Why is it 12? Yeah. Hence greatest, right? It's got to be the greatest one of them. The greatest of those factors. So yeah, sure. Here you could rate this as, this is 1, 2, 3, 4, 6, 8, 12, 24. All those numbers go into 24. 36, we've got 1, 2, 4, 6, 9. I forgot 3. 12, 24. No, not 24. I'm crazy. 18. And 36. So out of these two rows of all factors, the largest of them, as Emily said, is 12. Easy, right, with numbers? Simply list the factors, figure out which factor is the greatest of them. Now, with variable expressions, the same thing has to occur. You have to list the factors of any of the variable expressions or variable terms and see which of them is in common. So if I have this, how about 6x squared and 15x cubed? What's the greatest common factor of those two terms? 6x squared and 15x cubed. So again, I'm asking what goes into each, right, Morgan?
3x squared.
3x squared, yeah. Because the top one could be broken into 3x squared times 2. And the bottom one is 3x squared times 5x. And again, see how I'm doing that. I'm taking 3x squared out, becomes 3x squared times 5x, because that gets back to here. If you don't know what's left after you take out your GCF, divide it by your GCF. That's how you get what's left. All right? 6x squared, which is right here, this divided by this gives you this. That's really where it comes from. This right here, divided by the GCF, gives you this, which is what's left over. So when we're doing this in this class, and you have to take a factor out in front, and you're trying to figure out what's left in those parentheses, just divide what was in the parentheses originally by your GCF, and it'll tell you what's left over. All right. So let's take a look at a first example of this. Oh, that's what I used for the first example. So let's change this first example up. Let's change this to 5y to the 4th plus 35y squared. Figure out the GCF and rewrite the expression with whatever's left over when you take out the GCF. So in case you're struggling with this mentally and you want to do it without being able to do it in your head, take a look up. 5y, 5y. It's in both terms. So what did I do on the board? What did I write out? What is that called again? When I write out all the smallest factors possible, what was that term? What is it?
Factor.
You're writing out the factors, but specifically, if you're writing out all the smallest factors, what was it again that Inigo helped us with earlier? Yeah, this is the prime factorization. Okay, obviously the y's you can write as y to the fourth and y squared over here, but I'm going to write them out separately so you can literally visualize this. So see what's in common between both of these expressions. 5 is in both. There's 2 y's over here, and there's at least 2 y's over here. So everything that's in both can come out. So a 5 comes out front, another y comes out front, and another y comes out front. Well, what's left over in the first one when I take out 5, y? What's left over in the first one?
2 y's.
Yeah. Y times y is left over. And in the second one, when I take out a 5, y, what's left over?
7.
Simply 7. Now, obviously, I'm not going to write it this way, right? This is kind of crazy that I'm writing it this way. So the way you would obviously write it would be by writing it as 5y squared times y squared plus 7. Okay? And if you check to see that this is true, how do you know your answer is right? That's the good part about this topic. You always know your answer is right by checking. How do you check? What is factoring really? It's the opposite of what? What's factoring the opposite of? Chandler? Distributing. You see that? Distributing, okay? See how this 5y squared? Distribute it back out. You get back to what you started with. Okay, you could always check your work after you factored something by just simply distributing it back out and seeing if you get back to what you had to start. Okay, simple so far? We should all be familiar with factoring, but let me know if there's something that you're not sure of before we go on to other stuff. Okay, so let's look at the next. We're going to look now at this part, and we're going to say, all right, recall that we have this rule. Remember that rule we wrote down at the top? We wrote it down when we were in section 4.2 or 4.3. And it said that if you have the quantity a plus b times the quantity a minus b, it turns out that the middle terms cancel, leaving you with simply a squared minus b squared. So I want you to take that rule that we wrote down for multiplication and apply it to factoring. So for example, let's take a look at part A here. Part A, we've got u squared minus 49. U squared minus 49. Where did that come from? What factors multiplied each other to give you u squared minus 49? Sarah?
U minus 7 and U plus 7.
Yeah, and how do you know that?
Because when you multiply it back, it's U squared minus 49.
Okay, that's one way, absolutely. You multiply it back out, you're going to get u squared plus 7u minus 7u minus 49. Absolutely, that's one way to remember, right? Multiplying it out. How else do you know that that's true?
If you square root, which is u, and then 49, you get the 7 because of the rule.
Yeah, now that, keep in mind that that happens to work, but you're not really square rooting, just so you know, okay? But you're right, you are taking the square root of each individual term, but you're not, remember, this, okay, you cannot square root this. Okay, keep that in mind. You cannot, because a square root, really, you get the same answer twice, and these are clearly not the same answer twice, right? Okay, so you're not really square rooting, but you're square rooting individual answers. Now, the reason you're square rooting individual parts of this is because of this rule that we had up here. See this rule up at top? Oh, that's too red. There's a highlighter function now. It's pretty cool. So if you take a look at the rule at the top there, we're told that the difference of two squares here could be written as a difference and a sum multiplied by each other of those individual components. So u squared is a perfect square, 49 is a perfect square. But part B, that's not true, right? Look at part B. 5x cubed is not a perfect square. 20x is not a perfect square. So what do I have to do before I can even start this? And I always have to do this, actually. Before I can start any problem of factoring, before I use difference of squares, sum of cubes, all that kind of stuff, factoring quadratics, I always have to look for something first. What's the something I look for first? Yeah, first take out the GCF. So out of 5x cubed minus 20x, what's the GCF in this case? What's the greatest common factor here? Will? Yeah, it's going to be 5x. Now, Jeff, tell me, what's left over if I take out this 5x here? What do I have left behind? What does this become?
X squared
Minus 4. Now, Jeff, what do you recognize? X squared minus 4, what is this an example of? Yeah, the difference of two perfect squares there. So once you've taken out that GCF, what are you left over with? You're left over with something that can be then factored further. This can be factored further. This cannot. If you didn't know this was left over, Jeff knew right away. He said, all right, x squared minus 4, he's got it. But if you didn't know, all you got to do is this. And this is like a mental thing. Ready? Divide every term by the GCF in your head. Well, 20x over 5x is simply 4. X is canceled. 20 over 5 is 4. The negative sign carries. The 5 and the 5 cancel. There's a 1 now. X cubed over x is x squared. So that's how you can tell what's left over in case you ever have trouble with that. Because really factoring is dividing through by that number. Okay, that's what you're like literally doing in your head. You're not actually doing it on the paper though. So as a result, I can rewrite this as 5x, and then what does x squared minus 4 factor into? X squared minus 4, what is that, Inigo?
X minus 2, and then x plus 2.
Good. Okay, whenever you have a difference of two squares, simply, as Danielle mentioned earlier, take the square root of each individual component to give you these numbers. One is positive and one is negative. Part C. Part C. And this one is already ready to be factored into difference of two squares. There's no GCF here. There's no GCF.
5r cubed minus 6 and 5r cubed plus 6.
Good, Jeff. Well done. Okay, we can see here that it's r to the 6th power. How do you get r to the 6th power in the beginning? It's r cubed times r cubed. That's what r to the 6th is. So write yourself a note, please. If the power is even, all you got to do is cut it in half. So if I had r to the 8th, it would be r to the 4th and r to the 4th. If I had r to the 12th, it would be r to the 6th and r to the 6th. Okay, the reason being is because really when you multiply two things with the same base, you add the exponents. 3 plus 3 gets you back to that 6. In practice, if you need to, FOIL that back out, distribute it back out, see that you get back to 25r to the 6th minus 36. Okay? Any questions on difference of two squares? Can I give you guys a more challenging one? Let's see how you can do. Let's say we've got 4 over 49 x to the 12th, minus 0.25 y to the 8th. Let's try and factor this one, please. 4/49 x to the 12th minus 0.25 y to the 8th. You could always start by doing that right away when you see that they're both perfect squares. How do I know these are both perfect squares, by the way? Am I right? Why, Sarah?
Because 0.25 is actually 1/4, and you can divide that into 1/8, and then 4 over 49, those are both, you can both like square root the numerator and the denominator.
Okay, just be careful. It's not 1/8 though. But you're right. The explanation was correct there. So we've got 4/49 x to the 12th. Well, you just simply look at the square root of that. What do you got, Chandler?
2/7 x to the 6 minus 0.5 over the 4.
And then obviously with a plus as well. And it's odd because, and I don't mean odd as in odd or even, but odd or weird, because you wouldn't think that 0.5 would be the answer when you take a square root of 0.25, right? And you said 1/8 originally, you divided it by 2, right? So it's weird because when you take a square root of a fraction or a decimal, the number gets larger. That was something that we talked about earlier in the year. If you square a fraction or a decimal, the number actually gets smaller. And if you didn't know that it was 0.5, as Sarah said, convert 0.25 as 1/4. Square root of 1/4 is 1/2, and 1/2 is really 0.5. And then the exponents, we just literally cut them in half each. Okay? All right, let's take a look at this. Factor by grouping. Factor by grouping. Has anyone heard that before? The term factor by grouping? You might have seen it, maybe not named this way. Okay, but factor by grouping is to take a look at the terms and literally group them into little parts. Let's go through an example of this. So look at part A. This is, by the way, this is very useful when there are 4 terms. Write yourself a little note. When there are 4 terms is when this is useful. 4 terms. When there's 3 terms, it's a quadratic usually, and you're going to do other type of factoring. But 4 terms is where you can use factoring by grouping. So look at the first one, part A. We've got xy plus 3y plus 2x plus 6. Look at the first 2 terms. James, what can I factor out of the first 2 terms? Leaving me behind with? Good. And Alex, the second terms in red there, what can I factor out?
2
Leaving me behind with?
x plus 3.
Is that a coincidence or not? Probably not, right? What could I do next? What could I do next? All right, I started with how many terms, actually? Let's step through this, because this is not obvious. I started with how many terms? In the very beginning of the problem, how many? 4. 1 expression, but 4 terms, yes. So we started with 4 terms, and you can tell because there are 4 different parts separated by plus or minus signs, right? Now how many terms do I actually have? Be careful.
2.
Just 2. This is term number 1. Let me point with the marker so you can see later. This is the first term. That's the second term. Now, when I had these 2 terms, I noticed that y was in both, right? And I factored it out. And then, or James told us that. And then Alex recognized that there was a 2 in both of these, so he factored it out. Well, what's in both of these terms now? This is term number 1. This is term number 2. What's in both of them? It's obvious. What is it? X plus 3. So what should I do if it's in both?
You just write it as 1 term, and then you write x plus 3 multiplied by 1 plus 2.
Yeah, I should factor it out front. Take the x plus 3 and move it out in front. Well, if I take x plus 3 out of this one, I'm left with a y. Take x plus 3 out of this one, I'm left with the 2. So that's where Chandler's getting the second part of this, is simply y plus 2. So those would be your factors using factor by grouping. A technique that's not always used widely, but very useful, especially when you have 4 terms, especially when you have a quadratic whose leading coefficient is non-unity, right? It's not a 1. So if you have something like 25x squared plus something x plus something else, it's very useful to use this method, and we're going to see how that works. Okay, so again though, x plus 3 was in both terms. Factor x plus 3 out in front, leaving behind y plus 2. That comes out here. Okay? Try part B on your own. Try part B on your own. 10r squared plus 2rw. What comes out of that? James? 2? That's it? Something else. Again, what comes out of here is the question, right? A 2, but something else comes out as well. 2r. Isn't there an r in both? Right? The first one is r squared, but technically r squared is r times r, so you have at least an r in both. I'm going to see what's left in a moment. How about the second part? Can I factor anything out of the second part? -1 can come out. And let's show why that's true in a moment. So let's see, what's left when I factor out the 2r here first? What's left when I factor out the 2r? What am I left behind with? Will?
5r squared plus w.
5r just simply plus w. Be careful. Because you had r squared, right? So again, that's what I have. Now, if you didn't know that a -1 comes out of the next two, or if you didn't do it, it's okay. But factor by grouping only works if what's inside the parentheses is the same, right? X plus 3 was here and here earlier. So that's why Sarah took out a -1. Sarah said, wait, what if I do this? If I take out a -1, it makes this -5r minus w into positive 5r plus w. And then what you see in blue is the same, right? That's the reason you take out a -1 there. It's not obvious right away. It's not obvious, but with factor by grouping, you have to take something out. Even if you take out a 1 or a -1, you have to take it out. The reason being is now you can factor out the 5r plus w, and you can't forget about this -1. This becomes 2r minus 1 here. Now, what if I had switched the middle terms instead? Let's do this problem again with the middle term switched. So let's try it. We'll see if we get the same answer. 10r squared minus 5r plus 2rw minus w. So I switched up the middle two terms. Now what comes out of the first two terms? What comes out of the first two terms right here? Jenna?
5r multiplied by 2r minus 1.
5r leaving behind, good. 2r minus 1. 5r leaving behind 2r minus 1. And Morgan, the second part that's underlined in blue here, what comes out of that?
The 2w.
W, right? Because there's no, you need a 2 in both to take out a 2. You don't have a 2 over here. So the w comes out, what are you left with?
2r minus 1.
Yeah, and take a look. Now what we're noticing is that 2r minus 1 is our repeated factor, isn't it? Earlier, 5r plus w is repeated. But in the end, multiplication is commutative. So the answer I'm going to get from this is going to be the same thing. I'll write 5r plus w and 2r minus 1. But these are exactly the same thing. Okay, it does not matter which order I write them in because it's multiplication which is commutative. So the idea behind factor by grouping is that you want to take out a factor that is in both of the terms of the first two. In your homework, I think I gave you an example or two. You might even have a factor by grouping problem where there's 3 terms to factor out of. And it's a little bit trickier, but it's the same idea. You got to factor something out of the first 3 terms, not the first 2, if you have like 6 terms total. Okay? So you'll see that when you go through that. All right, let's see the last part, I think. Yeah, the last type of factor we're going to do for today. The factor we're going to look at is sums and differences of cubes, which is not easy. And the reason it's not easy is because, honestly, it needs to be practiced. If you don't practice it, it's not going to be a simple thing to do. If you do practice it, honestly, it gets pretty simple after a while. So the idea is this, and I'm going to have you guys memorize this form. It's not easy to memorize, but there's a simple way to do it. So if you have 2 things that are perfect cubes, as opposed to perfect squares, like earlier we looked at x squared minus 49 was one of our examples. That's not this. This is perfect cubes now. So if you have perfect cubes, it could be a sum or a difference. It's not just a minus sign. With perfect squares, it has to be a minus sign. So here we have a cubed plus b cubed. And that's going to equal the quantity a plus b. I'm going to do the plus first, right? It's going to equal the quantity a plus b times the quantity a squared minus ab plus b squared. So what I want to remember here is this. Here's how I remember how to factor this. If these are both cubes, keep the sign that it was for this, and switch the sign that it is for this. Again, if this was a cubed plus b cubed, it would equal a plus b, so you keep the sign, meaning it's still positive, and then all you do is switch this one right here, make that a negative. Okay, again, whatever the sign is between your cubes, the opposite sign goes in front of the term AB. That's all that's saying at the top. So if this was a minus here, what would it look like? If I had a cubed minus b cubed, what does that equal to, James?
A minus b is a squared plus ab plus minus b squared.
It's still a plus, actually. That's all right. The square terms are always positive. Look at the pattern up top. There's no plus or minus there, right? So where you see the plus or minus is where you need to switch the sign there. Okay, so those are the two different forms of difference in sum of cubes. This is clearly sum of cubes. This is clearly difference of cubes. So to do this, or to actually perform this operation properly, you need to identify what your perfect cube is. So look at part A. 8x cubed minus 27. 27 is a perfect cube, but what is it the perfect cube of? 3. And what about 8? What's 8 the perfect cube of? 2. And x cubed is the perfect cube of? X. So we start by doing this, and this is the easiest way to do this. Please trust me on this. Because in the beginning, yeah, it's easy, so you don't have to worry, but when it gets harder, you don't want to probably do this. So for part A, I would start by rewriting this as 2x cubed minus 3 cubed. Literally rewrite it with the cubes in place. This is not factoring, right? That is not factoring what we just did. All I've done is rewritten 27 as 3 cubed. I've rewritten 8x cubed as the quantity 2x cubed. Now, A is 2x. B is 3. Again, I'll point it out so you can see. Remember the formula told us if we have a minus sign here, we need something cubed. Well, this is A then, right here. This is A, and this is B. So if you need to do it on the side, you want to write down A is 2x, and B is 3. And then all you need to do from that point on is plug it in to these points in the factored form. So it's going to be 2x minus 3, parentheses over here, the quantity 2x squared plus 2x times 3 plus 3 squared. So you're literally taking the 3 and plugging it in wherever you see a B, and the 2x wherever you see an A. So that's A minus B times the quantity A squared plus AB plus B squared. Now, I'm overdoing the parentheses, I know I am, but I need you guys to recognize that the quantity 2x is squared, right? That's why I went a little overboard. Yeah, you need parentheses around the 2x to square, but the other parts, like the 3 squared, you could drop the parentheses. It's just 9, obviously. Okay, but the 2x, that entire quantity needs to be squared. So your answer becomes the following. 2x minus 3 times the quantity 4x squared, I just did cubes because we're on cubes, 4x squared plus 6x plus 9. That make sense? All you're doing is applying a rule. It's a simple rule to do this every time. Now, you might be saying to yourself, oh, could that quadratic be factored a little bit further? It never can. Write yourself a note. Because in the next section, we're going to factor quadratics. And when you do this, you're going to want to say, oh, can I factor this further? This will never be able to be factored. Okay? This term here will never, or this factor itself, will never be factorable. So what about part B? How about part B? Y cubed plus 1.
I have a question actually.
Yeah, ask.
Do you mean it can never be factored for just for the second term or for both terms? Like in the final list?
It would be both terms actually, because, unless, here's the thing, Chandler. If 8x cubed minus 27 could have had a GCF come out of it first, then you'll have a GCF that can come out of here. See what I'm saying? But I'm assuming that these already have no GCFs involved. But if you could take out a GCF in the beginning and you forget to, then at the end you'll have to take out the GCF of this term. But this will definitely never be factorable. Okay? Good question. So in part B, we have y cubed, so we can right away see that our cubed is y, right? A is y in this case. And 1 is really just 1 cubed. So this is really what we have for part B. we have y cubed plus 1 cubed. So as a result, A is y and B is 1. Okay, this is A and this is B right here. So go ahead and apply the rule. That's all you have to do. So we're going to have A plus B times the quantity A squared minus A times B plus B squared. Okay, the last one, just so you know the answer, you can check this. So, real quick, the last one, this is the example actually you asked. The last one, part C, if you look at part C real quick, you could take out a 2 and a U out of both. So if you want to try this and finish this up at home, first take out a 2U, leaving behind U cubed plus 27. And then the 2U you can leave alone. U cubed is a perfect cube. 27 is a perfect cube. So you're going to factor that portion. Okay, you have homework tonight. It's at the bottom of the notes. Please take a look at it.